Good day, we are Group 2 and will be discussing Lesson 3, Noise. I'm Charles David and I'll be your first reporter. What is a noise? Noise is any unwanted form of energy tending to interfere with the proper and easy reception and reproduction of wanted signals. Noise can also be any undesired voltage or current that ultimately ends up appearing in the receiver output. In a clearer description, noise is an error or undesired random disturbance of a useful information signal. Noise generated by electronic devices varies greatly as it is produced by several different effects. Results of noise may come from hiss or static, snow or confetti, bit errors, and signal loss. Hiss or static is a broadband noise that spans the entire audible spectrum but with more intensity in the high frequencies, so from a technical standpoint, this would be similar to the sound of blue noise. Snow confetti is a random dot pixel pattern of static displayed when no transmission signal is obtained by the antenna receiver of television sets and other display devices. The random pattern superimposed on the picture, visible as a random flicker of dots, is the result of electronic noise and radiated. So, while bit errors is digital transmission, is the number of received bits of a data stream over a communication channel that have been altered due to noise, interference, distortion, or bit synchronization errors. Lastly is signal loss. It is simply the loss of strength of a signal as it propagates over a medium. Generally, the term refers to loss of signal strength in guided media such as copper cabling and fiber optic cabling. Kinds of noise. These are correlated noise, intermodulation distortion, and uncorrelated noise. So, correlated noise is mutually related to the signal and cannot be presented in a circuit unless there is an input signal and is produced by nonlinear amplification. As you can see here, this is the input frequency spectrum where x-axis is the frequency and y is v. And this is the output frequency spectrum where the input signal is v1 and v2, v3, and v4 are the harmonic distortion, where harmonic distortion is unwanted harmonics of a signal. The correlation coefficient is a value between -1 and +1. That depends on how the two signals vary together. If they vary largely, independently, then the correlation is close to 0 and the signals are said to be uncorrelated. If the correlation coefficient is close to 1, they are strongly correlated, and if it is close to -1, they are strongly anticorrelated. Autocorrelation of a signal is a series that shows patterns within a signal. Each point of this series is the correlation coefficient of the signal with a delayed or advanced version of itself. Next is intermodulation distortion. The generation of unwanted sum and difference frequencies or cross products when two or more signals are amplified in a nonlinear device. Here, we have two inputs. This is the input frequency spectrum and this is the output frequency spectrum. So you can see V1, V2 are the two input signals. V difference and V sum are the intermodulation distortion, where V difference is F1 minus F2 and V sum is F1 plus F2. Intermodulation distortion between frequency components will form the additional components at frequency that are not just at harmonic frequency of either, like harmonic distortion, but also at the sum and difference frequencies of the original frequencies and at sums and difference of multiples of those frequencies. Intermodulation is caused by nonlinear behavior of the signal processing being used. Then, last kind of noise is uncorrelated noise. It present regardless of whether there is a signal present or not. It refers to noise that has a zero autocorrelation function, so every point in the noise signal is independent of every other point. So even if you have a signal values for a large time, you cannot predict the next value. So uncorrelated white noise is noise that is both uncorrelated and has a flat power spectrum. Whiteness of a noise refers to the flatness of its power spectrum. It is possible for uncorrelated noise to not be white but pink, or other colors based on the power spectrum. Gaussian noise is an example of uncorrelated noise, where Gaussian noise is common to every communication channels, which is statistically random region noise characterized by a wide frequency range with regards to a signal in the communications channel. So there are two kinds of uncorrelated noise. These are external noise and internal noise, where external noise is generated outside the device or outside the receiver circuit, while internal noise generated within the device or within the receiver circuit. Types of external noise. These are atmospheric noise, extraterrestrial noise, and man-made noise, where atmospheric noise is naturally occurring electrical disturbance that originated within the Earth's atmosphere. Next is extraterrestrial noise. Consists of electrical signals that originate from outside the Earth's atmosphere. This can be classified as solar noise or cosmic noise. Solar noise is directly from the sun's heat, while cosmic noise is from the stars. Lastly is man-made noise, produced by manufactured equipment such as automotive ignition systems, electric motors, and generators. Then next is types of internal noise. These are shot noise, transit time noise, and thermal noise, where shot noise is caused by the random arrival of carriers, holes, and electrons at the output element of an electronic device. Then, transit time noise shows us a kind of random noise within the device and is directly proportional to the frequency of operation. Then the last type of internal noise is thermal noise, associated with the rapid and random movement of electrons within a conductor due to thermal agitation. This is part of my report, and thank you for listening.
Hello, I'm Luis Rafael E. Lontoc from Group 2 and I will be discussing noise computations. Noise power. The average noise power is proportional to the absolute temperature of the conductor and to the bandwidth or spectrum of the thermal noise. Here is the equation for the noise power, where P sub n is equal to kTp. P sub n is the noise power in watts, T is the temperature of the conductor in Kelvin, B is the bandwidth of the noise spectrum in Hertz, and K is the Boltzmann's constant, which is 1.38 times 10 raised to negative 23 joules per Kelvin. Before we go on to the noise voltage, we will first consider this noise source equivalent circuit. Here is the noise source equivalent circuit. This is the resistor or the noise resistance, and this is the voltage across it, or also known as noise voltage. This is the load resistance, and this is the voltage across the load. From here we can see that the noise resistance is equal to the load resistance, and the voltage across this load is equal to the noise voltage divided by 2. Before we get the noise voltage, we will first compute for the maximum power transfer of the noise source. We will use the following components. The load resistance, which is equal to the noise resistance, and the voltage across the load, which is equal to the noise voltage divided by 2, stated earlier. Then we will use the power formula, which is P is equal to V squared over R. This is the power formula using these components, where this is the voltage, which is squared, divided by the resistance, which is the noise resistance. From here, we will get this equation. This is now the formula for the maximum power transfer of the noise source. From here, we can now compute for the noise voltage. But first, we will recall the power equation. Since the noise power is equal to kTB, we will substitute this, the power transfer equation. Now, we can now compute for the noise voltage. This is the final equation for the noise voltage, which is square root of 4 kTBR. Noise voltage is the RMS voltage of the circuit. Now we will get the RMS noise voltage due to several sources. First is the series combination. This is a circuit with series sources. This is the source 1 and source 2. From here we can see the first resistor is in series with the second resistor, and the voltage across this resistor 1 is also in series voltage across resistor 2. We will just get the summation of these components, and it will result to this simplified equation, which is the total noise resistance and the total RMS noise voltage. Here is the formula for the series combination. This is the resistance and this is the noise voltage. For the parallel combination, you can see that first source is in parallel with the source 2, and the voltage across this resistor is the same as the voltage across this resistor, and it will result to this simplified circuit. This is the formula for the parallel combination.
Jeremy Yumol from Group 2 and I will be discussing about power spectrum density, signal-to-noise ratio, noise factor, and noise figure. Power spectrum density or noise density. Power spectral density is a particularly suitable function with which to describe machine surfaces since it clearly depicts and separates any strong surface periodicities that may result from the machining process. So, power spectrum density is a figure that determines the amount of noise contained in a specific bandwidth, and it is also the average noise power per hertz of bandwidth. So here we can see the formula for power spectrum density or noise density. So in the given formula, NO, which is the noise density, is equals to P sub n, which is the noise power, over B, which is the bandwidth of the noise spectrum. The next topic is about signal-to-noise ratio. A signal-to-noise ratio compares a level of signal power to a level of noise power. It is most often expressed as a measurement of decibels. Higher numbers generally mean a better specification, since there is more useful information than there is unwanted data. Specification for signal-to-noise ratio can be found in many products and components that deal with audio such as speakers, telephones, headphones, microphones, amplifiers, receivers, radios, CD or DVD or media players, PC sound cards, smartphones, tablets, and more. However, not all manufacturers make this value readily known. So, a signal-to-noise ratio is a relative measure of the desired signal power to the noise power. So, here is the formula for signal-to-noise ratio in decibel form. So, S over N sub dB is equals to 10 log PS, which is the signal power, over Pn, which is the noise power, or it can also be equals to 20 log Vs, which is the signal voltage, or the V sub n, which is the noise voltage. So the next topic is the noise factor. Noise factor is the measure of degradation of the signal to noise ratio in a device. It is the ratio of the signal to noise ratio at the input to the signal to noise ratio at the output. Since the signal to noise ratio at the output will always be lower than the signal to noise ratio at the input, the noise factor is always less than 1. The lower noise factors result in better performance of A devices. So here is the formula for noise factors, which is F equals to Si, which is the input signal power, over Ni, which is the input noise power, all over So, which is the output signal power, over No, which is the output noise power. The next topic is the noise figure. Noise figure is a metric used to indicate the quality of amplifiers. It is the decibel representation of the noise factor that determines the sensitivity of the amplifier is decreased to an incoming signal due to its internal noise. It is defined as the ratio of total output noise power to the output noise due to the input source. The lower the value of the noise figure, the better the performance. So here we can see an image for the process of the noise figure. On the left side, we can see the input signal power over input noise power as it enter a device for it to be tested. As it been tested, it goes out at the right side as the output signal power over output noise power. So, given a formula, the formula for noise figure is equals to 10 logarithmic S sub I over N sub I all over S sub O over N sub O. So thank you guys for listening, and that's all for my assigned topics for lesson 3.
Hello, I am Marcos Pelayo, and this is the continuation of lesson 3.2. This is about noise computations. Lesson 3.2, Noise Computation. Reactance noise effects. The significant effect of reactive circuits on noise is their limitation on frequency response. The equivalent bandwidth to be used in noise calculations with reactive circuits is B sub EQ equals pi over 2 multiplied by B sub 3 decibels, where B sub 3 decibels is equal to half power bandwidth, hertz units, and BEQ is effective bandwidth, also hertz units. Equivalent noise temperature. Noise temperature. Equivalent noise temperature TE is not the physical temperature of the amplifier but rather a theoretical construct which is an equivalent temperature that produces the amount of noise power. It is very useful in microwave and satellite receivers. Noise temperature is expressed as TE equals T multiplied by the quantity of F minus 1, where TE is equivalent noise temperature expressed in Kelvin. T is temperature reference value of 290 kelvins, and F is noise factor. The next one is noise due to amplifiers in cascade. Freeze formula. Overall noise factor of n stages. F total is equal to F1 plus F2 minus G over G1 plus F3 minus 1 over G1 times G2 plus F4 minus 1 over G1, G2, G3, and so on and so forth, where F is equal to noise factor and G is power gain. The next is overall noise temperature of n stages, where TEQ is equal to T1 plus T2 over G1 plus T3 and over G1 times G2, and so on, where T is noise temperature. The formula for overall noise resistance is REQ equals R1 plus R2 over A1 squared plus R3 over A1 squared times A2 squared, and so on, where A is equal to voltage gain ratio and G is power gain ratio. The next is shot noise. Shot noise is a form of internal noise which is due to the random variations in current flow in active devices such as tubes, transistors, and diodes. IN is equal to square root of 2BIQ, where IN is RMS noise current in amperes, and Q is charge of an electron, which is equal to 1.6 times 10 raised to negative 19 coulombs. Sample problem. Problem. Compute the noise figure of a receiving system with a noise temperature of 150 degrees. The solution is we use TEQ is equal to 150 degrees Celsius plus 273 equals to 423 kelvins. We add the 273 to convert the Celsius to kelvins. Next is T is equal to 290 K, and F is equal to TEQ over T plus 1, where the answer is 2.4586. The formula is derived from the noise temperature equation. And the final answer is noise factor is equal to 10 log F. The answer is 3.9069 decibels. So that's it, guys. Thank you for listening to our video presentation about noises, and hope you guys learn a thing or two. Thank you again.